Imagine placing a hyperactive dog inside a fenced-in suburban yard. Inside those borders, the dog stays in constant motion, pacing the perimeter or running in circles near the porch. This physical setup mirrors a mathematical sequence, a never-ending list of numbers following a specific rule, stepping forward one at a time. Mathematicians look past the first few entries to see where the numbers lead after millions or billions of infinite steps. Every sequence eventually follows one of three paths. It escapes the yard, it paces back and forth, or finally lies down to rest. Understanding a sequence is simply a matter of identifying that final destination. Consider a list: 1, 4, 9, 16. On a number line, the gaps between these points grow larger with every step. These values continually increase, with no maximum limit to hold them back. They eventually soar past billions and trillions, moving further away forever. Because this list breaks through any theoretical fence and wanders off, we classify it as a divergent sequence. A sequence without a mathematical boundary is destined for endless wandering, never reaching a stable final value. We can also create a sequence that repeats: 1, -1, 1, -1, stretching out into infinity. Here, the value jumps rhythmically back and forth. This is a bounded sequence. It never exceeds 1 and never drops below -1, keeping it trapped inside a mathematical fence. Even when a sequence is trapped, it can remain perfectly restless. This bouncing behavior inside a boundary defines an oscillatory sequence. To describe this more precisely, mathematicians use the term limit point, a specific location the sequence visits repeatedly, forever. Our bouncing sequence is torn between two different limit points, 1 and -1. It returns to both of them an infinite number of times. A bounded sequence with multiple limit points will pace back and forth forever, unable to choose a single final destination. Other sequences home in on one specific spot. Take the fractions 1/2, 1/3, 1/4, and so on. These values move progressively closer to 0. This list is also completely bounded. Its highest value is 1/2, and the fractions will never drop below 0. Unlike the pacing sequence, these numbers get infinitely closer to 0 and never leave that immediate neighborhood. Because the numbers crowd around one resting spot, the sequence has a unique limit point. A sequence that is both fully bounded and possesses one unique limit point is convergent. Convergence is the act of finally lying down to rest in one exact, unchanging spot. A sequence only truly settles when it has two things: a boundary that keeps it from escaping, and a single, unique spot where it chooses to stay. If a sequence moves toward infinity without a boundary, it is divergent. If the sequence is trapped but bounces between different numbers, it is oscillatory. And if the list is trapped and zeroes in on exactly one final number, it is convergent. The next time you see a list of numbers heading toward infinity, look to see if they are escaping, pacing, or settling. When you identify that destination, infinite lists stop looking like random data and start revealing a clear final shape.